Okay, hello, everybody. I'm here to show you how to use Excel to actually create these viscoelastic models that you need to for the laboratory exercise. So the first thing, this is for the stress relaxation foam sample 1 test. I have a number of I first plotted my time and force, which were my experimental results. I converted this force into the experimental stress. We can see that I plotted it on the left here. The stress decreases over time. First thing to do is calculate the relaxation time, which is the amount of time it takes to reach a relaxation of 62.3% of the maximum stress difference between the maximum and the steady state value. I'll let you guys struggle with that a little bit on how to calculate that. So I plotted the experimental results here, and I want to create a Maxwell, Kelvin-Voigt, and standard linear solid model to estimate or approximate model the experimental results. So for the Maxwell model, I've entered in this actual equation over here. For the Kelvin-Voigt, I've entered in this equation, standard linear solid, this one. And the parameters from these models, time is your experimental time for each time step you were able to calculate data for, TR, relaxation time, and then any variables such as E for the Maxwell model I've presented here, as well as the RMS E values for each model, and I'll let you figure out how to actually calculate RMS. I've started out with guessing that E for each one of these models is 10 megapascals, and I've plotted the experimental results and also the Maxwell Kelvin-Voigt standard linear solid model approximations using my initial guess of E is 10 megapascals, and we can say that they're not doing a very good job here. They're way below the actual experimental results. The question is, so I can manually change each one of these E. So let me bring this down here so you can see what's going on. If I change E in any one of these, let's say I go up to 15, you can see that the corresponding model actually makes a change, and it changes the RMS error value. And the smaller the value here, the better the model fits the experimental results. The question is, I don't want to keep trying this a million times until I get the optimal RMS value. So we have to use something called the Excel solver function. All Excels are able to do this, but it's not in any one of these data tabs. What you have to do is you have to go over to Options, go to Add-ins, Manage Excel Add-ins, and then add in the solver. And this pops up in the Analysis tab under Data. The solver allows us to do some really nifty stuff that you may find useful also in additional courses. What we can do is we can set an objective, and our objective right now is we want to reduce this RMS E value for our Maxwell model, and we want to find the minimum, and we want to do that by changing the modulus here. So when I press solve, what it's actually going to do is it's going to keep playing around with E until it minimizes this value. I want to keep it, and you can see that it actually did change my Maxwell value, and it did reduce my RMS. Now we cannot get any better than this for the Maxwell model, even though you can see it's not doing a very good job. So I will repeat this process. I want to reduce my RMS value for my Kelvin-Voigt model by changing my E for Kelvin-Voigt. You can see that it changed the model here, and we've also reduced my RMS value significantly. I'll do this once again for the standard linear solid model. Oops, sorry. By changing both E1 and E2. And we can see that this really reduced my RMS value, and that matches the eyeball test, saying that probably the standard linear solid model is matching us quite perfectly. So I'm going to let you figure out how to implement these long equations for the stress relaxation tests and the creep tests, and how to calculate RMS values. One thing to note is your E needs to be generally a close approximation beforehand, otherwise the solver cannot find it. So for instance, if I start at maybe, it's easier to demonstrate this with the standard linear solid. If I guess like 1,000 or 10,000 and I guess 1 here, if I hit the solver, it's already set up for this. You can see now that the standard linear solid did not do a good job approximating. We can see that RMS value is quite high. So we want to kind of already start with a good model, but it doesn't need to be perfect in order to solve for it. So let's try that again. You can see this did a much better job. So play around a little bit till you get your modulus values close to what close-ish for a good model approximation, and then use the solver. The only other thing I want to add is people may be wondering, well, Ryan, why are you using scatter on the experimental results and a straight line on the models? Well, we know that the models are mathematical formula and not experimental results, so that they actually are continuous and connected between the results, but the experimental results actually are not continuous between, because they're subject to a number of different errors and we don't know necessarily what's happening in this time. So that's why I've had have two different types of lines on this graph. So I hope this helps. You'll need to complete this exercise for both the stress relaxation for sample 1 and sample 2, as well as creep on the turkey skin. Just let you know that this is not the foam sample you'll be using in lab, so you don't get a head start with the data that I've collected here. Okay? I hope this helps. Thank you.